Hi guys, this is a channel that explores integration, and we are going to solve some very complex integrals in the coming future. But first we should start by getting ourselves familiarized with the rules of integration. And I am going to start with the basics of integration and what it means. So when we think about integration, we can think about it like this. Let's say I have a graph, and let's say I have the line y equals x. And it looks like that. That's the line y equals x. And we're going to only focus on the first quadrant for the time being, so quadrant 1. And the definition of an integral and the proper notation is this. We say the integral from a to b of f of x dx. The a and the b represent the bounds of which we're integrating from. So for instance, if I wanted to integrate this function y equals x, and I wanted to integrate from x equals 0 to x equals 5, I would write that as the integral. From 0 to 5 of f of x, and then I have to substitute in my function. So my function is x dx. And I can represent that on the graph like this. So at x equals 5, we're going to be at the point 5, comma 5. So here's 5, comma 5. Let's just say that's 5, comma 5. And then we're also going to be integrating at the point 0, comma 0. These are our boundaries. And the integral simply represents the area bounded by the x-axis and the line at which you're integrating about. So this right here, this area under my curve, is my integral value. Now, we'll learn how to evaluate this integral later, but this is what we think about when we think about integration. And how calculators solve integral problems is they evaluate tiny rectangles within the shape if it's a complex shape. So we know this is a triangle, so we could actually just use 1/2 base times height to evaluate the integral of this expression. And that's a simple shape, but sometimes you're going to have like quadratics or parabolic curves or cosine or sine. And what calculators do to calculate that is they take an infinite sum of rectangles under that curve that sum exactly to the integral value. And that's what this integral notation represents. It actually represents sigma. And sigma is the sum of infinitely small rectangles. And that's what this dx is. It's telling me that I'm taking infinitely small widths and infinitely small lengths, and I'm multiplying those rectangles, or I should say adding them. I'm adding those infinitely small rectangles, and I get approximately my integral value. So the basics of integration include the sum and difference rule, and the sum and difference rule states that the integral from a to b of f of x plus or minus g of x, so two functions, dx, equals the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And we are indeed allowed to separate it like that. That's why it's called the sum and difference rule. So if I have two functions that are being added or subtracted in my integrand, this is what we call the integrand of an integral, what's inside it, I can then separate it and individually integrate each function on the same bounds. Then the constant multiple rule states that the integral from a to b of kf of x dx equals k times the integral from a to b of f of x dx. And there's also, so that's the second rule, when we multiply by a constant of a function, we can take out that constant and put it in front of the integral. Then we also have the reverse interval rule, which states that if I have an integral from a to b of f of x dx, it is exactly equivalent to the negation of the boundaries flipped of the same function. And we'll get into why this works later on. And then we have the zero length interval. And I'm not, this is sort of an interesting rule, but all it states is that, so I'm going to write it out, the zero length interval. And it states that the integral from a to a, so the same bounds, of f of x dx is simply 0, which makes sense, right? If we're integrating from the same boundary to the same boundary, well, there's no area under that curve. It's simply just going to be 0. And then the last rule is going to be adding intervals. So let's say I have the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Well, that's actually just going to equal the integral from a to c of f of x dx. So if I'm going from a to b and then b to c, that's almost the same thing. That's actually just the same thing as going from a to c, because this top part, I'm integrating within that b, so the b's can just eliminate. And those are the basics of integration. And in the next video, we will get into more complex examples of integration and dive deeper into integrals.